Welcome to The Explainer. Today we're going to talk about a really strange mathematical secret. It's hidden in plain sight, and it's a pattern that can actually tell you if the numbers you're looking at are real or fake.
All right, let's start with a puzzle. Picture this. You're handed this massive spreadsheet, okay? Thousands upon thousands of financial transactions. How in the world could you spot a lie in there? I mean, without checking every single line. It sounds impossible, right? Well, turns out there's a trick.
The answer, believe it or not, lies in this really bizarre and weirdly powerful pattern, and you find it in all sorts of real-life numbers. We're talking stock prices, the lengths of rivers, population data, you name it.
Okay, so if I were to ask you to guess how often each digit, 1 through 9, shows up as the first digit in a big list of numbers, what would you say? You probably think, well, they're all equally likely, right? So about an 11% chance for each one. Makes perfect sense. It's intuitive. But it's totally wrong.
The reality is, it's not even close. The distribution is wildly skewed. In a ton of naturally occurring data, the number 1 shows up as the first digit about 30% of the time. Think about that. Almost a third of all numbers start with a 1. And the number 9? It barely makes an appearance, showing up less than 5% of the time. This crazy, counterintuitive pattern? Well, that's Benford's law.
And this isn't a new discovery. This strange phenomenon was actually first spotted way back in the 1880s. An astronomer named Simon Newcomb noticed something funny. The first few pages of his logarithm books, the ones that started with the digit 1, were way more worn out and dirty than the pages at the back. Kind of weird, right?
So, to put it formally, Benford's law is just the observation that smaller numbers like 1, 2, and 3 show up way more often as the first digit. But here's the really crucial part. This law really only works for data that spans multiple orders of magnitude. And what that means is we're talking about numbers that range from, say, the tens, into the hundreds, then into the thousands, and even higher.
Okay, so the big question is, why? Why on earth does this happen? What's with this bias towards small numbers? Well, the secret isn't really about the numbers themselves. It's all about something called proportional growth.
Here's the key. You have to stop thinking about numbers as just static points on a line. Instead, I want you to picture them as dynamic things, values that are always growing and changing over time.
And honestly, the best way to get this is with a visual analogy. It's not about the destination, it's about the journey. A number takes as it grows. This right here illustrates the idea perfectly. Think about it. For a number to go from starting with a 1 to starting with a 2, let's say from 100 to 200, it has to literally double. That's a 100% increase. But to go from starting with an 8 to starting with a 9, like from 800 to 900, it only has to grow by about 12.5%. See the difference?
So because it has to cover so much more ground, proportionally speaking, a number just spends more time with a 1 as its first digit than any other number. It's a much longer journey. So if you just take a random snapshot of a dataset that's growing like this, the odds are just way higher that you're going to catch a number while it's in that 1 phase.
And this simple little mathematical quirk, it's become this incredibly powerful tool. I mean, for anyone who's trying to spot fake data, it's basically a natural lie detector. And the places it's used are pretty amazing. We're talking about sniffing out accounting fraud, auditing election results, digging into national economic data, heck, even monitoring crypto transactions for sketchy activity. See, the thing is, when people just make up numbers, they tend to spread the first digits out way too evenly, and that's a dead giveaway that they're breaking this natural law. So put yourself in the shoes of an auditor for a second. Instead of going through every single line item, which would take forever, you can just run this simple, elegant first check. You literally just count up the first digits from all the data and see how it stacks up against the Benford's curve. Now, a perfect match doesn't guarantee everything's okay, but a big deviation? Oh yeah, that's a huge red flag telling you exactly where you need to start digging. But, and this is a big but, the law is not a magic bullet. It doesn't work everywhere. And honestly, knowing when it doesn't apply is just as important as knowing when it does. So like we said, it works beautifully for data that spans those big ranges, stock prices, populations, that kind of thing. But it completely falls apart for data that's stuck in a narrow, constrained range. Think about human heights, right? Or IQ scores. Most people fall within a pretty tight band. It also doesn't work for numbers that are just assigned in order, like invoice numbers, or numbers that are totally influenced by our own psychology, like all those prices that end in 0.99. So the key takeaway here is pretty simple. The spread of the data is what matters most. For Benford's law to really kick in, the dataset has to be wide, covering a big range of values.
If the data is narrow, the law it's not going to work.
Benford's law it's such a fascinating reminder that underneath all the chaos and randomness of the world, there's often this hidden mathematical order. It's a pattern that was hiding in plain sight the whole time. And it really makes you wonder, right? What other profound hidden patterns are out there, just waiting for us to discover them?